Hey there, and welcome to the section on equilibrium. Equilibrium's a interesting topic, and it's often a tough topic to kind of get your head around initially. At this stage, I hope that you've had a look at the other YouTube videos that are up there on the website or linked underneath. If you haven't, please just take a look at it, even if you just look at it at 2-speed, because it's important to get this kind of visual concept down, and the graphic artists will do a very, very good job of trying to explain to you, like to give you an impression of what equilibrium is. If you have had a look at the videos, thank you. And we want to just recap a couple of points to take away from this. So first of all, you should have gotten the idea that from equilibrium that most reactions are reversible, in that they can go forward but that they can also go backwards. So we can start off with our reactants that will be turned into products, and these products can actually react with one another to be converted back into reactants. The TED Talk video had a description of two people coming and smashing together, and then one person's arm was joined to another person's face, and then the people with missing arms, or the people with an arm on their face, could bash into one another again and reconvert themselves back into normal human beings. So it's saying that most reactions are this way. They can go both forward as well as backwards. So reactions can be reversible. Secondly, equilibrium occurs when there's a state of balance. In other words, that when the rate of the forward reaction is equal to the rate of the backwards reaction, that's when we have what is known as chemical equilibrium. And the concentrations might not necessarily be the same. So the concentrations of products and reactants might not necessarily be the same. It might be 50-50, 60-40, 30-20, so on. But what does happen is that since the rate of the forward and backwards reactions are equal, this means that the number of particles being converted into product is the same as the number of particles being converted into reactants every second. So that means that the concentration of products and reactants are going to be constant. So the example that can be given, so unfortunately, like, our video is going to be a little bit more technical than the others, but anyway, unfortunately what this means, or fortunately for us, depending on how you look at it, we can put some chemistry to this. So for example, if we start off with calcium carbonate and have a solid calcium carbonate base, we know that there's a reaction of the decomposition of calcium carbonate into what's known as calcium oxide, which is a solid, and carbon dioxide in gaseous form. So there might be a box here, and there's a block of calcium carbonate. So calcium carbonate. And we know that this is decomposing into carbon dioxide and calcium oxide. So what I'm going to do is I'm going to show that in the initial part, what's going to happen is there's going to be a little bit of carbon dioxide being formed. Okay, this is day 1. Day 2, what happens, or like moment 2, as the reaction progresses, the amount of carbon dioxide in this grows bigger, and the amount of calcium oxide here, let's draw a little bit of calcium oxide here, that also increases. Calcium oxide. So calcium oxide and carbon dioxide increase as time goes on. And as time goes on, of course, what happens is the amount of calcium carbonate will decrease. So we will get the amount of calcium carbonate. So this is what it used to be, like this, right? And now it's like this. The amount of calcium carbonate decreases. So if we were to draw a graph illustrating this, what we would see is that if I said this is concentration and this is time here, what we would see is we'd see the concentration. I know that this is a solid, so there's no real actual concentration, but just for example's sake, let's say the concentration of calcium carbonate will slowly decrease as time goes on, and the concentration of carbon dioxide and calcium oxide, so calcium oxide plus carbon dioxide, will slowly increase as time goes on. As time goes on, however, what happens, so this is when we see a predominantly forward reaction occurring. But as time goes on, what happens is that we'll see that the carbon dioxide over here will start reacting with the calcium oxide over here, and they will react to reform calcium carbonate. So what will happen is that the carbon dioxide and calcium oxide actually react with one another to reform some calcium carbonate over here, right? So even as the calcium carbonate is being converted into calcium oxide plus carbon dioxide, right? The carbon dioxide and calcium oxide is also working to reform calcium carbonate. Okay, so when that happens, what happens is that eventually the rate at which we combine carbon dioxide and calcium oxide to form calcium carbonate becomes the same as the rate at which calcium carbonate decomposes and forms carbon dioxide and calcium oxide. So what we'll see in that situation is when the rates become equal, the concentrations of each of these don't change. So the concentrations of each of them become constant like that. Okay, so at this point where they've become constant, we've reached what's known as equilibrium. So we can write EQ like 1 there. Okay, so that's the first idea there. Let's have a look at this idea again, but let's see it from the, Let's see it from the point of view of reaction rates. All right, so what we talked about here is we've seen the concentration become constant over time. What happens to the reaction rate? Well, at the start, right, if we were to look at this reaction at the start, what would we see? So this time what I'm going to draw is I'm going to draw a rate and time graph. Over here at the start, what we see is we see a block of calcium carbonate. So we could say that the surface area of calcium carbonate, or the concentration of calcium carbonate initially, is very high. So that means the rate of reaction for the forward reaction, so let's say this is forward reaction. Remember, just reminding us that the reaction was what? It was calcium carbonate decomposing to calcium oxide plus carbon dioxide. So the rate of the forward reaction initially is going to be really, really high. So because we've got a high concentration, okay? But as time goes on, what happens is that this calcium carbonate decomposes a little bit. So it decomposes and decomposes and decomposes and decomposes and decomposes. And instead, we get more and more carbon dioxide and more calcium oxide. So as the forward reaction goes, we run out, or we use up calcium carbonate, and we start producing calcium oxide and carbon dioxide. So these are the ones here that we start producing, okay? So as time goes on, let's have a look at calcium carbonate. It gets smaller and smaller and smaller, okay? So calcium carbonate gets smaller. So as calcium carbonate gets smaller and smaller and smaller, what happens? Well, the concentration of calcium carbonate, or the surface area, will get lower and lower, which means and we know that when that happens, we get what? A reduction in the rate of reaction. So the rate of reaction will go down and down and down. At the same time, what's happening is that calcium oxide and carbon dioxide, well, their surface area and their volume, or their concentration, will be increasing. So if we have an increase in the concentration of calcium oxide and carbon dioxide, the reaction calcium oxide plus carbon dioxide forms calcium carbonate. That reaction gets faster and faster and faster. So if I change my color over here and slowly increase, what we'll draw this over here, what we'll see is we will see that this is the rate of the backwards reaction, which is calcium carbonate joining carbon dioxide to form calcium oxide joining carbon dioxide to form calcium carbonate. The backwards reaction will increase as time goes on. So what we see over time is that we get the rate of the forward reaction decreasing and the rate of the backwards reaction increasing in this particular example, and this results in us reaching a point where the rate of the forward and the backward reaction are the same over here, right? So here the rate of the forward and backwards reactions are the same, so this is different. So yeah, it's the same. So therefore, this is where we have equilibrium. All right. So note that Here, we've noted that the equilibrium occurs when the rate of the forward and backwards reaction is equal or the same, right? But we also note that equilibrium occurs when the concentration of products and reactants are constant. So it's important to note this difference. This is what I was just about to mention before. So the difference is that the concentrations are constant, right? Which means that they don't change, but they're not necessarily the same. The concentration of calcium oxide and carbon dioxide is not necessarily the same as that of calcium carbonate, but the rate of reaction of the forward and backwards reaction are the same, okay? So it's important to note that difference. So in this section, I just really want to quickly show you that in the concentration time graph, we see that the concentration, let's say these are reactants. Remember, what they'll look like is different for different reactions. We'll look at this in class. So reactant, and this is, let's say, product. So we can see that the concentrations become constant. So in this situation, they become straight lines, but they're not the same. So you can see that the straight lines are separated from one another. However, when we have a look at the reaction rate, what happens here is that the rate of, let's say this is the forward reaction. It's not necessarily the forward reaction, but it can be. And this is the backwards reaction. What we can see is that over time, the rates of the forward and the backwards reaction become equal at equilibrium, and the concentrations of the reactants and products become constant at equilibrium. Okay. And that ends our introductory section. We'll look at all the calculations in class. Thanks for watching.